complicated than what we started with, at the advantage of having a standardized way of talking about these particular equations, so that we no longer have the ambiguity involved of looking at two equations side by side and deciding whether they are equivalent or not. In this particular video, we're going to kind of undo that process. So we're going to start with an equation, and we're going to try to shrink it down to be as small as it possibly can be. We're going to minimize these equations. We're going to simplify these equations. So let's take a look at our equation from the previous video that is in sum of minterms form. It's very complicated compared to what it can be. In fact, we already saw a simpler version of this particular expression. So what I'm going to do in this video is apply various Boolean algebra properties to this expression in an attempt to make it as small as possible. I'm not going to work exactly in reverse of what I did in the previous video. I'm going to take a slightly different route to try and explore a few other types of Boolean algebra properties that we may or may not have seen in action before. Okay. So for starters, when I look at an equation like this and I want to minimize it, when I want to try and simplify it as much as possible, the first thing that I'm going to do is try to identify terms that are very similar to one another but not exactly the same. So specifically, I'm looking for terms that are identical except for one input value is different. To give you an example of what I'm looking for, this very first term here, a, b, c, d naught, and this term right here, a, b naught, c, d naught, vary by only one input, specifically b. So this term has b as true, this term has b as notted, so false, right? So what I'm going to do is actually group those terms together. Here I've added parentheses just so that we can see that these are grouped together. It's actually not required to use parentheses, but it makes it easier visually to see what I'm working on by having these parentheses in here. And then if you recall from our previous video, we relied a lot on that identity property to create sum of minterms form. Well, we can also rely on that identity property to undo sum of minterms form and simplify particular expressions. So what we're going to do is actually factor out the common parts of these two particular terms, which is everything except for the b, right? A, c, and d naught are in common with these two terms. We're going to factor those out. And what we're left with is this. We have a, c, and d naught factored out. B or b naught left over. You'll recognize that from the previous video as being the or identity. This is true. This is simply a true statement. So this value can actually fall out. We don't need it anymore. These two terms can just go away. And so here's what we're left with. We've already eliminated one term, right? So we still have a long ways to go. Another common thing that I'll do when I'm looking at minimizing a particular equation or a particular expression is look for common values that exist in terms. So if I look at all of the terms after the first one, starting with this second term here, I'll notice that they all have a b in common. Every single one of these has a b in common. If you watched the previous video where we created these minterms, that shouldn't be a surprise to you. You actually know why that b exists in all of those terms. But that actually works in our favor when simplifying this. So I can actually factor that b out of each of these particular terms, which gives me something like this. So you'll notice I factored the b out. None of these terms now include a b anymore. We've factored it out. And then I'll repeat the process that I did at the beginning of the video. I'll look for terms that are very similar to each other, except for one input being flipped. So for example, what I have in terms of groupings, I have a, c naught, d naught, and then down here I also have a naught, c naught, d naught. So the input value that differs there is a, right? Here it's true, here it's knotted. So I'll group those two terms together. And I'll do the same thing with some other terms. Here's what it looks like after I perform that grouping. So a naught c d is grouped with a naught c naught d. So the difference here is that c input, right? And then finally, here's the grouping where again the difference is this c input, a c naught d, a c d. You'll notice I had an odd number of terms here, so I have one term left out. That's okay, just tack it on the end. And again, remember, these parentheses aren't exactly required, but I do think that it helps visually distinguish these groupings as I'm trying to simplify this expression. Once I have these groupings, I'll do exactly as I did before, where I'll factor out the common parts, which leaves me with those OR identities. In fact, since I've already done that once, I don't have a slide showing those OR identities, only the results of the factorization, which is this. So I factor out the commonalities and I eliminate that OR identity like we saw at the beginning of the video, and here's what I'm left with. Right away, hopefully you notice that these two terms in the middle also follow that rule that we just applied. They're exactly the same except for one input. A naught is here, A is here. So I can apply that same rule to these particular terms, and then what I'm left with is just this. So you can see we've already shrunk this particular equation by quite a bit, but we're not quite at the simplest form just yet. To keep moving in the right direction, I'll again rely on factoring. I see that this term here and this term here have a d naught in common, so I'm going to go ahead and factor that d naught out. Here's the result, d naught, and then what's left over. And then you'll probably recall from class last Thursday that we actually proved something about this particular expression that I see inside of the parentheses here. Whenever I see an input and its opposite ANDed with something else, like I see here, I can actually remove the input from this particular case. So C naught or A naught and C is actually equivalent to the same expression with the C removed. And so in this particular case, I can just remove that C, as we see here. And if you're paying really close attention, you actually see that same configuration appear again. Here I have D ORed with D naught and some other stuff, which means I can actually just remove this D naught entirely and be left with this other stuff. And so here's our result. We're getting even simpler now. We've only got a couple steps left, right? And so to finish this out, I noticed that actually this first term here, A, C, D naught, has the same terms involved as what's inside the parentheses, but opposite. So C naught, A naught, and D are the opposite of A, C, and D naught. And also the operations are the opposite as well. Here they're ANDed together, and here they're ORed together. Well, we also proved in class last Thursday that De Morgan's law can apply to more than just two values. It can apply to any values that I would like. So I can actually apply De Morgan's law to this set of three values here, this set of three terms, which gives me this. A, C, D naught, not, right? And if you'll notice, I have that same configuration that I saw twice previously now, where I have a set of values ORed with some other value and the opposite of that particular set of values, which means that this term, A, C, D naught, not, can actually just fall out entirely. And so here's what I'm left with. A, C, D naught, or B. This is the simplest form. This is this expression minimized into its smallest possible form. Now you may be wondering at this point, well, wait a second, this actually isn't the equation that we started with when we went down this whole path. Our original equation actually had more terms in this. It looked a little bit different than what we see here, and you're right, it does look a little bit different. So in the next slide, what I want to do is actually explore whether or not these two expressions are in fact equivalent or not.